How do they do this? Well, for this, we first of all need to have a look into what a so-called double layer capacitor actually is. We're now looking at a system where we have two electrodes which are separated by a separator, and these electrodes are surrounded by the electrolyte I just introduced you. Again, an electrolyte always contains positive and negative ions which are dissolved in a solvent. So what you will get is you will create a so-called interface, which is basically just a contact area between your electrode and your liquid electrolyte. And exactly at this contact area, you will observe something called the double layer effect. How does this double layer effect express itself? Well, let's first go through it theoretically. If you apply a voltage to your electrodes, you will form three different layers. The layer number one is the so-called inner Helmholtz plane, or IHP. At the IHP, you have solvent molecules in a preferential orientation. Because these solvent molecules, they feel the electric field created by the electrode and they orient accordingly. Additionally, you can, for example, also have specific ion adsorption. The second layer is the so-called outer Helmholtz plane, or OHP. Here you have non-specifically adsorbed counterions together with a hydration shell. A hydration shell is simply a shell of molecules surrounding an ion. And we have layer 3, which is a so-called diffuse layer. In the diffuse layer, the ion concentration is represented by a gradient which is different from the bulk solution. Okay, this was now very theoretical. Now let's have a look how it actually looks in practice. So here we have a simple model where we have an electrode which is connected to our negative pole. So we create a negative charge here on our electrode. Now the first layer is, as I told you, the inner Helmholtz plane. This inner Helmholtz plane has these kind of blue circles with the arrow in here. And what this visualizes are solvent molecules. And we assume that as a solvent, we have water in this case. So looking at water, we have this red oxygen atom here and these two white hydrogen atoms. This is the concept I told you about earlier. The oxygen likes electrons much more, so it tends to pull the electrons from the bonds to the hydrogens to itself, creating a negative partial charge on the oxygen and a positive charge on the hydrogen, therefore creating somewhat what you might call a minimized electric field, or simply a dipole. And this kind of molecule arrangement is now represented by this kind of blue circle with the arrow. And the water molecules can now be polarized because your electrode creates an electric field, and water has a high permittivity, so it will orient opposite to this field to counteract this field. And this leads to the fact that you will always observe a preferential orientation of the solvent, especially when it's close to the electrode. As a consequence of that, the permittivity of water is significantly reduced in this kind of layer. We've seen earlier in this plot that the relative permittivity of bulk water is around 80.1. In the inner Helmholtz plane, the permittivity of water is only 6. And this is due to the forcing of this orientation. If we now go out one layer, we're in this outer Helmholtz plane. So here water molecules are still strongly polarized from the electrodes, but they are also polarized from cations, so from positively charged ions. Water still has a preferential orientation, which is now given on the one hand due to the negatively charged electrode down here, but also due to the positive charge here. Notice that the arrow is orienting away from the positive charge, as this partially positively charged hydrogen atoms want to orient away from the positive charge, because as we've learned earlier, positive charges repel each other. again, even though we are a little bit further from the electrode, you see that bulk permittivity is 80.1, and now in this outer Helmholtz plane, we still are at a relative permittivity of around 30. So we still haven't reached the bulk value yet. And the third layer is the so-called diffuse layer. In the diffuse layer, the ion concentration is represented by a gradient, which is different from the bulk solution. So we have an ion concentration, which increases the further we go away from the electrode. So we will have more and more negative charges the further we go away from the electrode, which makes sense because these negative charges are usually repelled from this electrode. So we will find them further away. Also, the cation concentration will decrease because if we're close to the electrode, cations or positive ions will be attracted towards the electrode. But the further we go into the bulk, the more we will approach this bulk value, which is actually equal charges on both sides. So at the last layer, we're then in the bulk electrolyte, and here we will have bulk anion concentration and bulk cation concentration, which basically means that assuming that we have one positive anion for one negative cation, that we find equal concentrations for both ions if we are far enough away from the electrode. I want you to recognize from this explanation that here we are not looking at a simple physical system anymore. We're now looking at a complex system where we have various distances, where we have various areas, and also where we have different relative permittivities. So the simple formula for the capacitance, which was epsilon 0 times relative permittivity times the area of our electrode divided by the distance, is actually composed of various different contributions rather than one set of values.